In exercises 35 to 50, find A, the interval of convergence of the series. For what values of x does the series converge? B, absolutely, and C, conditionally. Now this one is geometric. If you plug 0 in, you get 1, then x plus 5, and then x plus 5 squared, and so on. A sub 1 is 1, but more importantly, r is x plus 5. So the absolute value of x plus 5 has to be less than 1. We have negative 1 is less than x plus 5 is less than 1. And then when we minus 5, we get negative 6 is less than x is less than negative 4. So the interval of convergence absolutely so far is negative 6 to negative 4. But let's check the endpoints. For x equals negative 6, we get n equals 0 to infinity of negative 1 to the n. So negative 1 to the n. Well, that's equal to 1 minus 1 plus 1 minus 1 plus 1 minus 1. So you're going from 0 to 1 to 0 to 1. That is diverging. So that diverges. For x equals negative 4, we get n equals 0 to infinity of 1 to the n. And that's just 1 plus 1 plus 1 plus 1, keep on going. So that also diverges. That's headed to infinity. So A, the interval of convergence is negative 6 to negative 4. B, absolute convergence is negative 6 to negative 4 because we took the absolute value. It's part of the geometric series test. And letter C, conditional convergence, none. Same instructions for this one. This one is not geometric, so we're going to do the ratio test. The limit as n approaches infinity of absolute value of 3x minus 2 to the n plus 1 over n plus 1, and then times n over 3x minus 2 to the n. We have the limit as n approaches infinity of, let's see, we have a 3x minus 2 on top. And then that's going to be times n over n plus 1. Now when we do the limit on n, we get 1. So the absolute value of 3x minus 2 has to be less than 1. We have negative 1 is less than 3x minus 2 is less than 1. Let's add 2. We get 1 is less than 3x is less than 3. And then we get 1/3 is less than x is less than 1. So the interval of convergence so far absolutely is 1/3 to 1. Let's check our endpoints. X equals 1/3. And we get n equals 1 to infinity of 1/3 of 3 is 1. 1 minus 2 is negative 1. We get negative 1 to the n over n. Now this converges conditionally by alternating. Well, it's converges conditionally, and it's the alternating harmonic series. For x is equal to 1, the other endpoint, we have n equals 1 to infinity of 3 times 1 is 3 minus 2 is 1 to the n over n is 1 over n. And this diverges by harmonic series. Harmonic series. All right, so now to answer the question, letter A, where does this converge? Well, it converges at 1/3, and it converges to 1, but not at 1. Letter B is absolutely. This converges absolutely from 1/3 to 1. And C, where does it converge conditionally? At x equals 1/3. Same instructions for this one. This is not geometric, so let's do the ratio test again. We have the limit as n approaches infinity of absolute value of 4x minus 5. And if we plug n plus 1 in for n here, we get 2 times n plus 1 plus 1. So 2n plus 2 plus 1. So this is going to be 2n plus 3 over n plus 1 to the 3 halves, and then times n to the 3 halves over 4x minus 5 to the 2n plus 1. Limit as n approaches infinity, and then we have 2 extra 4x minus 5s. So 4x minus 5 squared. We can write the n's as n over n plus 1 to the 3 halves. Now when we do the limit on n, this is 1, and 1 to the 3 halves is 1. We get absolute value of 4x minus 5 squared is less than 1. Well, since this is being squared, we don't really need the absolute value. And when we square root both sides, the square root of this squared is the absolute value of 4x minus 5. That has to be less than 1. So right here we can say, well, if we have this, if this is squared and has to be less than 1, then what's on the inside must be less than 1. In order to square a value that ends up being less than 1, the original, what you're squaring, has to be less than 1 as well. Negative 1 is less than 4x minus 5 is less than 1. Let's add 5. We get 4 is less than 4x is less than 6. Yep, and then divide by 4. 1 is less than x is less than 6/4, which is 3 halves. Now one of these should make the parentheses 1. One of those should make the parentheses negative 1. Let's check the endpoints. X is equal to 1. We get a brand new problem. So it's like we're creating this brand new problem. We got to decide how this converges. When we plug 1 in, we get 4 minus 5, which is negative 1. We have negative 1 to the 2n plus 1 over n to the 3 halves. Well, 2n plus 1 is always going to be odd. And if it's always odd, then every term is going to be negative. We can make this negative. N equals 1 to infinity of 1 over n to the 3 halves. And then if we took the absolute value of this, then we can say, well, p is equal to 3 halves, which is bigger than 1. So this is going to converges absolutely by p series. Let's check the other endpoint. X equals 3 halves, and so it's like we have a brand new problem again. N equals 1 to infinity of, 3 halves. 4 divided by 2 is 2. 2 times 3 is 6, so 6 minus 5 is 1. This is 1 over n to the 3 halves. So p is equal to 3 halves, which is greater than 1. And this one converges absolutely by p series. So letter A, where does this converge? Well, it converges from 1 to 3 halves. B, where does this converge absolutely? From 1 to 3 halves. And where does it converge conditionally? Nowhere. So none. No values. Same instructions. This is not geometric, so again, we're going to do the ratio test. Limit as n approaches infinity of the absolute value of 2 to the n plus 1 over n plus 1. And then this is x minus 1 to the n plus 1. We'll multiply by the reciprocal, so we have n on top, 2 to the n on bottom, and then x minus 1 to the n. Limit as n approaches infinity. And then we have an extra 2 on top and an extra x minus 1. That's times n over n plus 1. The limit on n is going to be 1. The absolute value of 2 times x minus 1 is less than 1. Negative 1 is less than 2 times x minus 1 is less than 1. Divide by 2. Negative 1/2 is less than x minus 1 is less than 1/2. And then add 1. 1/2 is less than x is less than 3 halves. So one of these should make the parentheses 1. The other one should make this negative 1 in the end. I guess not the parentheses, but when we do all the canceling. Let's try x equals 1/2. We get n equals 1 to infinity of -1 to the n plus 1. So that will alternate. And then 2 to the n over n. And 1/2 minus 1 is -1/2. So this is going to be, we could write it like this, -1/2 to the n. But we could also say that, well, that's -2 in the denominator. We could write it like that also. Then when those cancel out, we get -1 to the n. So this becomes n equals 1 to infinity of -1 to the n plus 1 times -1 to the n over n. Well, if this is, let's see, if we plug 1 in here, we get 2. So this is going to be a positive 1. And then when we plug 1 in here, that's going to be a -1. Then when we plug in 2, that's going to be a -1. And this is going to be a positive 1. So this ends up being an alternating, it's the alternating harmonic series. So this converges conditionally by alternating harmonic series. Let's test x equals 3/2, and let's see what we get. N equals 1 to infinity of -1 to the n plus 1. 3/2 is, let's see, 3/2 minus 2/2 is 1/2. That's 2 to the n over n times 2 to the n. It's really 1 to the n over 2 to the n, because this ended up being 1/2 when we plugged 3/2 in. Those cancel, and this is n equals 1 to infinity of -1 to the n plus 1 over n. So this also converges conditionally by alternating harmonic series. So A, where does this converge? Well, it converges from 1/2 to 3/2. B, where does it converge absolutely? None. And C, where does it converge conditionally? At x equals 1/2 and x equals 3/2.